Hello students, welcome back to session 7 of linear transformation class. So in the last class you have studied what is meant by a nilpotent linear transformation and two important lemmas related to this, and also you have studied what is meant by an standard, what is meant by a nilpotent of index k, and we also studied what are the standard nilpotent matrices. Now let us take up the continuation part of nilpotent transformation, which is one of the important theorem. Let us discuss this now. Okay. Now look here. So this is suppose T belongs to A of V is nilpotent. Suppose T belongs to A of V is nilpotent of index of nilpotence n1. Suppose the transformation T belongs to E of V is nilpotent of index of nilpotence n1. Then a basis of V can be found such that the matrix of T in this basis has the form mn1 0 0 etc 0 0 mn2 etc and so on mnr. What are these n1 n2 etc nr, where n1 is greater than or equal to n2 greater than or equal to and so on greater than or equal to nr, and where n1 is n1 plus n2 etc nr is equal to dimension of V over f. Dimension of V over f. Okay, understand this? Now, so this is like, say, now look here. Suppose here I will take T is nilpotent of index say 10. T is nilpotent of index 10 means T power of 10 is 0, T power of 9 cannot be 0, T power of 11 is certainly 0. Now, so then a basis of V can be found such that the matrix of T in this basis is, say this is according to this, what is that? First one is M10. N1 is here 10. So M10 means what? This one is a 10 cross 10 matrix. 10 cross 10 matrix. So nilpotent matrix. What will happen? So now suppose V is of dimension M10 means, so transformation has 10 cross 10 matrix means the dimension of the vector space V must be how much? Dimension of V is equal to 10, because there should be 10 number of basis elements V1, V2 etc. V10. Now what I do is, V being, say I will explain the hypothesis in the beginning itself. Say V being split, suppose I will split this V as V1 plus say W. V is equal to V1 plus W. Say V is equal to V dimension of V1 is say 3. So dimension of V1 is say 3, and dimension of W becomes what? Dimension of W becomes leftover is 7. Okay. So then you know from the previous theorem, previous lemma, that this the matrix of this will be becomes, say here matrix of, say this is M10, say this is the other matrix will be what? M7. This is the matrix of, so this is a matrix of V1 and this is a matrix of W. Okay, according to previous theorem. Now look here, I will split again W as, now again split W as, okay, W as, say I will put W as V2 plus V3. I will split W as direct sum of V2 plus V3. Here also it is a direct sum. So V2 plus V3. V2 is of dimension say 2. V2 is of dimension say 2. Dimension is 2. V3 is of, what is the leftover? 7 minus 2 means it is dimension is 5. Okay. Then what will happen about what about the matrices? So the matrix becomes, first one is M10 already there, but now I split M7 as V2 plus V3. So suppose this is of dimension 2 and this of dimension 5 means what you get? This is M2 you get, say I will try it like this, M2, and there is M5. Okay, understand now? M10, M2, M5. Again I will split this, I will keep this as it is and I will split this. Okay, and I will split V3 as V4 plus V5, direct sum of V5. So this is of dimension say 2 and this is of dimension 3. Okay, then what about dimension is 3? Then what about the matrix? So M10, next is M2. Okay, next we have splitted M2, M5 being splitted as M2 and M3 again. M2 dash, say I'll write because its dimension is 2. Okay, and last one is M3. Okay, now again I split V5 as V6 plus V7. V6 is of dimension 2, V7 is of dimension 1. Dimension is 2, dimension is 1. Then the corresponding matrix becomes M10, next is M2, next is M2 dash, next is M3 being split as M2, again M2 double dash, and this is last one is M1, say M1 dash. So understand now? So this is the matrix, how it looks. This is 10 cross 10 matrix, this is 2 cross 2 matrix, this is again 2 cross 2 matrix, this is again 2 cross 2 matrix, this again 1 cross 1 matrix. Okay, or accordingly we can split say M10, M9, M7 likewise. But total, the order of this matrix should be, total is what? 10 cross 10 only. It says 10 cross 10 only. Okay, understand now? So this is about the thing. Okay, this is all about what we have discussed. Okay, so this is a very lengthy and interesting result. Say let us take up the, now I highlighted the what is happening in this theorem. I have highlighted in the beginning. So now let us go formally to prove the required result. By step I will go now. Step 1. What is the step 1? Now they were given t is a nilpotent of index n1, means t power of n1 is 0, but t power of n1 minus 1 is not 0. Therefore there is a vector. If this is a non-zero transformation, every non-zero transformation maps non-zero vector to non-zero vector. Therefore t power of n1 minus 1 is not 0, means there is a vector v belongs to v such that t power of n1 minus 1 of v is non-zero. This one is non-zero. Okay. Now clearly the vectors v1, the vectors v, t of v, etc. t power of n1 minus 1 of v. How many elements are there? Total how many elements? n1 number elements, because v is there here. So t power of n, total number of elements is n1, are clearly linearly independent over f. Because look here, if you consider the linear combination of these above, so this is equal to 0 implies, say suppose this is 0, means if you show all the coefficients are 0, then becomes they are linearly independent. Suppose not, means some alpha is are not 0, then what will happen? Let alpha s be the first non-zero alpha. Let alpha s be the first non-zero alpha means the previous alpha is are all zeros, means alpha is 0 for I less than s. All other terms before alpha s are zeros. So alpha s is the beginning. So alpha s, okay, here alpha s, if I take alpha s into, what is the next term? Alpha s into t power of, yes tell me, alpha s into t power of s minus 1 plus alpha s plus 1 into t power of s, and so on. Likewise alpha s into t power of s minus 1 of v plus alpha s plus 1 into t power of s of v. So t power of s minus 1 is common in every term, so I taken outside and write the remaining term. This into this is equal to 0. Now alpha s is non-zero means by the previous lemma this is invertible. This is invertible means this has a inverse. It has a inverse means this cannot be 0. Okay, 0 element cannot have a inverse. This cannot be 0 means what is the possibility? T power of s minus 1 of v is equal to 0. T power of s minus 1 of v is 0 means what? But we have assumed that alpha s is the first non-zero element, first non-zero alpha. Now therefore what will happen? T power of s minus 1 of v is equal to 0. Now since s is less than n1, this contradicts the fact that t is nilpotent of index n1. Minimum is n1, t power of n1 is 0, minimum, that is n1. T power of n1 plus some element, some terms may be 0, but not less than n1. But here we have seen that t power of s minus 1 of v is 0, means it is contradicting our hypothesis that t is a nilpotent of index n1. Why this contradiction arises? Due to our assumption that there are some non-zero alpha i's in the linear combination. Therefore, there should not exist any alpha i's which are non-zero, means all alpha i's are zeros. All alpha i's are zeros means what? This must be linearly independent. Okay. Now these are linearly independent. How many elements are there here? n1 number of elements are there. If n1 number of elements are there and they are linearly independent, and these are, and v is of dimension s and t is of nilpotent of index n1 we have. Therefore we'll take, look here, we'll take v1 to be the subspace of v spanned by these linearly independent vectors v1, v2, etc. vn1, that we call it as v1 is v, v2 is t of v, etc. vn1 is t power of n minus 1 of v. There are n1 number of basis elements. Then definitely v1 is invariant under t. You can verify this. And t induces a linear transformation t1 on v1, which has a matrix. First matrix, what is that matrix? First matrix is mn1. Understand this? So it is like m10. So then v1 is invariant under t and induces a linear transformation t1 on v1, which has a matrix mn1. Let us come to the step 2 now. In the step 2, we will prove one lemma. So this lemma says, look here, if u is an element of v1 such that t power of n1 minus k of u is 0, where k lies between 0 and n1, then tk of u naught is equal to u. Tk of u naught is equal to u for some u naught belongs to v1. For some u naught belongs to v1. Look here, for this, now u belongs to v1 means u is a linear combination of basis elements of v1. So therefore I can write u as alpha 1 v plus alpha 2 into other basis t of v, etc. alpha k into t power of k minus 1 of v plus alpha k plus 1 into tk of v, etc. The how many basis elements? Alpha n1 into t power of n1 minus 1 of v. So now this implies you applied t power of n1 minus k on both sides. T power of n1 minus k of u is equal to alpha 1 into t power of n1 minus k of v plus alpha 2 into t power of n1 minus k, already 1 is there, n1 minus k plus 1 of v, and so on. After n stages, what will happen? T power of n1 comes, t power of n1 is 0, so all other terms become 0. T power of n1 up to t power of n1 minus 1 will not be 0, for other terms it is 0. Therefore alpha k into t power of n1 minus 1 is the last element. But t power of n1 minus k of v, t power of n1 minus 1 of v are linearly independent over f. Why? Because these are linearly independent means these are subsets of a linearly independent set. Therefore they are also linearly independent. Therefore they are linearly independent means what? These alpha is must be zeros, means alpha 1 is 0, alpha 2 is 0, etc. alpha k is 0. And so if they are zeros, then u can be written as, up to here u is this one. So alpha k must be 0 means u can be written as alpha k plus 1 into tk of v, alpha k plus 2 into t power of k plus 1 of v, and so on, alpha n1 into t power of n1 minus 1 of v. So that I can write it as, look here, that I may write it as tk of u. Tk of u is common in every term. So tk of u naught. What is u naught? Yes, u naught is nothing but first term alpha k plus 1 of v plus and so on alpha n1 into t power of n1 n k number tk I taken out, means k if you taken out, what it becomes? T power of n1 minus k minus 1 of v, which definitely belongs to v1, because this definitely belongs to v1. Understand now? So this is the proof of step 2. Next, let us take up the step 3. So step 3 says there is a subspace W of V. There is a subspace W of V invariant under T such that there is a subspace W of V invariant under T such that V is the direct sum of V1 plus W. First stage, splitting of V as the direct sum of subspaces. V1 already there. Now I split this as W. Okay. First stage is, in the example, M10 can be written as M3 plus M7. This is like 7. Okay. So now let W be the subspace of V of large possible dimension such that V1 intersection W is 0 and W is invariant under T. We will show that V is the direct sum of V1 plus, because V is the direct sum of V1 plus W means what? V is the sum of V1 plus W, and V1 intersection W must be 0. Already we have assumed that V1 intersection W is 0. Therefore, it is enough to show that V is the sum of V1 plus W. That I am going to show it now. Suppose V is not the sum of V1 plus W. Then what will happen? There are some elements in V which are not here. So that is taken to be Z. There is a element Z belongs to V such that Z doesn't belong to V1 plus W. Since T power of N1 is 0, T power of N1 is 0 means T power of N1 of any element, say Z, is also 0. But 0 belongs to where? V1 plus W. Okay, and so now this belongs to V1 plus W. Suppose K is the largest power of T such that, T K of Z belongs to V1 plus W. Means what? K is the largest power means Ti of Z doesn't belong to V1 plus W plus for I less than K. Thus Tk of Z is equal to what? Tk of Z is equal to, this belongs to V1 plus W means what? So Tk of Z is equal to U plus W, where U belongs to V1 and W belongs to W. Okay. Then what will happen if I assume like this? Then T power of N1 of Z. T power of N1 of Z can be written as T power of N1 minus K plus K. Means T power of K of Z I taken out inside. So this becomes T power of N1 minus K of Tk of Z. Tk of Z is what? U plus W. But T is linear. Therefore T power of N1 minus K of U plus T power of N1 minus K of W. Definitely, okay. This one V1 is also invariant under T, W is also invariant under T. Therefore, these elements belongs to V1, this element belongs to W. Therefore, T power of N1 of Z belongs to V plus W. This implies, look here, this implies, but T power of N1 of Z is what? 0, because T is an nilpotent of index N1. So it is 0 means what? What will happen? This term is equal to negative of this term. So this is equal to T power of N1 minus K of U is equal to minus T power of N1 minus K of W. But both belongs to T power of N1 minus K of U belongs to both. This is equal to 0 belongs to both means this belongs to the intersection. So these elements belongs to the intersection means T power of N1 minus K of U is equal to 0, because 0 is the only common element in V1 and W. Therefore this must be T power of N1 minus K of U is equal to 0. Okay, answer this. This is equal to 0. By step 2, if this happens, T power of N1 minus K of U is 0. By step 2, what will happen? Tk of U naught is equal to U for some U naught belongs to V1. Therefore what about Tk of Z? Tk of Z becomes U plus W. Implies Tk of Z is equal to U means what? You just now taken U means Tk of U naught plus W. Let Z1 is equal to Z minus U naught. Then where Z1 belongs to? Z1 is equal to Z minus U naught means, so Z1 belongs to V1 because both are belongs to V1. And Tk of Z1 is equal to Tk of Z minus Tk of U naught. Tk of Z minus Tk of U naught is, according to this, Tk of Z minus Tk of U naught is W. So W belongs to W means Tk of Z1 belongs to W. Tk of Z1 belongs to W. Now W is invariant under T. Therefore Tk of Z1 belongs to W means Tm of Z1 belongs to W for all m greater than or equal to K. Understand now? So this is a element which belongs to x belongs to w, means t of x also belongs to w, t square of x also belongs to w, and so on. Therefore Tm of z1 belongs to w for all m greater than or equal to k. Next, split this again. Let w1 be the subspace of V. Let w1 be the subspace of V spanned by w and the vectors z, t of z1, etc. tk minus 1 of z1. Let w1 be the subspace of V spanned by w as and z1, t of z1, etc. tk minus 1 of z1. Okay. Since, look here, since z1 doesn't belong to w, since z1 cannot be lies in w, and since w is contained in w1, therefore dimension of w1 certainly greater than dimension of w. Dimension of w1 is greater than dimension of w. Also, we have proved tk of z1 belongs to w and w is invariant under t. Therefore, tk of z1 belongs to w, w is invariant under t means w1 must also be invariant under t. W1 must also be invariant under t. If you want, we have shown this here. So tk of z1 belongs to w implies t of tk minus 1 of t of k can be written as t of tk minus 1 of z1 belongs to w, but this belongs to t of this one belongs to where? W in turn is contained in w1, implies t of element of w1 is contained in w1 means w1 is invariant under t. Okay. Now, so by the maximality nature of w, so we have taken w is the subspace of V of possible maximum possible dimension we have taken. Okay, so by the maximality of nature of w, there must be an element of the form w0 plus alpha 1 z1. These are the bases: w0 plus alpha z1 plus alpha 2 z2 and so on, alpha k t power of k minus 1 of z1 is not equal to 0 in w1 intersection v1, where w0 belongs to where? W, and where not all alpha k's are zeros. Otherwise what will happen? 0 is not equal to w0, because w0 is a non-zero element that belongs to w intersection w1, which is 0 means what? Which is a contradiction, right? So non-zero element belongs to the intersection which contains only 0 means what? This is a contradiction. So for this, let alpha s be the first non-zero element. Then w0, previous terms are 0 means alpha s minus 1, alpha s minus 2 up to alpha naught they are all up to alpha 1 they are all zeros, means w0 plus, so among these terms up to alpha s terms are zeros. So I taken w0 plus alpha s plus 1 into t etc. alpha k into t power of k minus 1. Among these, first element is what? Alpha s is the first element means what? Alpha s into t power of s minus 2. Alpha s into t power of s minus 1. Okay, one index less than this. Okay, what will happen? w0 plus alpha s into t power of s minus 1 is there, s minus 1 of z1 is there, that t power of s minus of z1 is taken as common factor from this. Definitely this belongs to v1. Since alpha s is not 0 again, by step 2, so this is invertible. This is invertible means it has an inverse. Let us take R be the inverse of this. Let us denote by capital R as a inverse of this. Then it's a inverse means this is a polynomial in T, therefore the inverse must also be polynomial in T, means R is a polynomial in T. Thus W and V1 are invariant under R. W and V1 are invariant under R. Therefore from the above, so what you can write? If you apply R on this, R into W0 plus, look here, R into W0 plus, this is element, it has an inverse R means R, this into R is must be equal to what? 1. This element is invertible and it has inverse, this is like you take S, it has an inverse R into S is what? 1. Therefore only remains is t power of s minus 1 of z1. T power of s minus 1 of z1 belongs to, right answer is contained in v1 means R of v1. but V1 is invariant under R, therefore R of V1 is contained in V1 implies V1 itself. This implies T power of S1 minus T power of S minus 1 of Z1 belongs to V1 plus RW, which is contained in V1 plus W. This implies what? T power of S minus 1 of Z1 belongs to V1 plus W. Since S minus 1 is less than K, since S minus 1 is less than K, this is not possible because we have assumed that K is the largest power of T such that Tk of Z belongs to V1 plus W. Okay. So therefore the step 3 follows. Next, let us come to the final step. Final step, here only we will consider the actual proof of the theorem. This is very simple. See here, by step 3 we can be written as V1 plus W, where W is invariant under T. Using the basis V1, V2, etc. Vn of V1 and any basis of V as a basis of V, because the basis of V1 and basis of W are combinedly the basis of V. So using the basis of V1 and any basis of V and any basis of W as a basis of V, the matrix of T as of the form. First one is what? Mn1, as I already explained in the beginning itself. Mn1 0 0 A2. What is this A2? A2 is the matrix of the transformation T2, which is the linear transformation induced by T on W. Okay, T2 is the linear transformation induced by T on W. So Mn1 0 0 A2. Next, what do? You split again A2, you get Mn2 and so on. Okay, look here, that also I explained. Say, since T power of N1 is equal to 0, T2 power of T2 definitely power of N2 is also 0 for some N2 definitely less than or equal to N1. You repeat the argument used for T on V for T2 on W. So what are the argument just now we have discussed for T on V? You just use the same arguments for the transformation T2 on W. Then again we can decompose W as we did for V. Continuing this way, we get a basis of V. Continuing this way, we get a basis of V in which the matrix of T is of the form Mn1 0 0 0 Mn2 etc 0 0 Mnr, where first one is of dimension N1 plus N2 etc Nr is equal to dimension of V. Okay, because size of the matrix is n cross n, total is n cross n, where n is the dimension of V. Understand this? This is a very important theorem. Okay, thank you for listening.